Hello, everybody. Before I welcome our guest speaker, I'd like to just announce real quick that Magnimind Academy is about to begin its machine learning mini bootcamp, which is a free bootcamp that will teach you the basics of Python and some other algorithms for machine learning through hands-on experience and our excellent instructor, Yasan Saran. I'd also like to invite those who have not already done so to go check out and subscribe to our YouTube channel, Magnimind Academy, where we upload all of the recorded sessions of these talks so you can watch them on your own time. Also, please comment any questions you have on YouTube or just let us know any thoughts about today's talk in the comment section below. All right, now I would like to welcome Tyler Bettilyon, who will be presenting his talk, Machine Learning in Databases, Learned Indexes, Hash Tables, and BTrees. At Magnimind, we strive to find speakers who can deliver talks like these filled with current information and fresh perspectives to go along with our data science education programs. These programs are designed to build the fundamental knowledge you need for a career in data science, and we aim to impact those, all of the careers that we can and as many people as possible. Whether it's refining skills with our mini boot camps or starting an entire career change with the support from our mentors, Magnimind has something to offer for anyone. Tyler joins us from an extensive background of data science education as well as software engineering. After approximately 2.5 years as an educator for various programming and data science companies, Tyler founded TEBS Lab, a new programming education endeavor that seeks to bring computer education to a broader audience. As you can probably tell by the title of today's talk, Tyler has a wide range of expertise on many different subjects pertinent to data science and programming in general. Today's talk will be mainly on some of the more specific applications of machine learning and a few of its uses. We at Magnimind are extremely excited to host him, and we would like to ask you now to give your full attention to Tyler.
Hi everybody, thanks for showing up. I'm going to share my screen real quick. If you'd like to follow along on your own, the slides I just pasted into chat, and just for posterity, I shared this at the beginning, but I'll share it again now. This talk is based on a 2018 paper. It was a collaboration between Google and MIT, which I've also just shared. It's really interesting stuff. I love this topic because it is a really neat intersection of classical computer science topic, indexing, and machine learning, which obviously is so hot right now. Super interesting stuff. So, a little bit about me before we dive right in. My name is Tyler Bettilyon. Like the hosts say, I've been working in technology for many years. I've been teaching for longer than that. I worked at some startups that you really don't care about. And now I work for myself at TEBS Lab. You can find us at that website or on Medium and Twitter. We write a lot. We share a lot of free educational materials. So, for your interest, there's a great free all-in Python introduction to deep learning that you might want to check out after this talk. If, deep learning is something that's interesting to you, a bunch of really useful like Python notebooks and collections of writing and reading material if you're interested in exploring that kind of stuff. Okay, that's me. What's this talk about? This talk is about database indexing. If you don't know much about database indexing, we'll get some of the very basics. But, preview, if you have a lot of data and it's all stored, oftentimes what you want to do is look up specific entries or ranges of entries in that data, and you want to be able to do that quickly. This is important for everyone basically who uses any kind of analytics software, but it's also important for machine learning people. We are consumers of indexes. If you have some kind of data pipeline, you need to be able to grab that data quickly, the particular data that you're interested in. Okay, we use indexes for this. So we're consumers, and now by the end of this talk, I'll convince you that we machine learning people could also be producers of indexes in the future, which has not been true so far. Okay. This is also a talk about the classical two indexing strategies. So if you didn't get like a computer science degree or take a databases course at some point in your life, then some of this will be pretty new information for you. We're not going to go too deep, but if you did take a databases class at some point in your life, this will be review. I'm not sorry for that. I think these are really interesting topics, and it's always fun to take another look at something a few years later. Okay, then finally, we're going to talk about this paper. The paper is called the case for learned indexes, and they propose some new interesting strategies with, a lot of caveats. This is still new and emerging research, especially 2 years ago when this paper was published. But a promising new direction for a field that has been more or less tapped out. There's not that many great, new, novel, exciting advances in the world of indexing because, well, basically, it's been around for so long. Where is the hand raising panel? I see that someone raised their hand. You can just type your question into the webinar chat, and I'll try and address it as it comes up.
We actually have a Q&A tab. This is better for us to answer questions.
Sorry, what was that?
There is also a Q&A tab. Q&A.
Oh, yeah. I'm clicking on the QA tab, but it's not showing. Oh, here it is, over here. Yeah, okay, I have the QA tab open now as well. So you can type it into chat or punch it into the QA, and I'll try and answer it as it comes up. But if you raised your hand, just type it into the QA. We can't really turn on your mic, okay? Okay, so anyway, exciting paper. We'll wait for that question to come up and I'll answer it then. But exciting paper, and we'll talk about what kind of preliminary research they've done into applying machine learning to solve the problems that classical indexing structures have previously solved. And then finally, we'll look at some of the benchmarks that they ran and compare the trade-offs of these learned indexes and look towards the future. There are some interesting, especially hardware advancements that make the current existing structures kind of less appealing as time goes on. Maybe you've heard, maybe you haven't heard, but Moore's law, the law that has previously guided how fast CPUs will increase their speed, is dead, or at least is dying. And GPUs and parallel data instruction sets are really kind of the future of high performance computing, or at least it really looks that way right now. And ML workloads can capture those benefits, and these classical indexing structures really can't, or at least not nearly as well. So there's some interesting future-looking potential for these kinds of algorithms as AI workloads continue to get super optimized on the hardware side. Okay, so that's kind of where we're going. Now that I've told you what I'm going to tell you, I'm going to start telling you what I'm here to tell you. So first, just a quick review of indexing. Indexing is something that helps us to, if we have a large collection of data and we need to find specific items within that data, we don't want to have to scan through the entirety of the hard drive, all of the database records, to find that data. So when we're querying and we have specific queries like, where's the index for all of the people named Tim? Or where are the records for everyone who was born within a certain date range? We use indexes, right? So in our database, we've got a whole bunch of rows. Every row is stored in the hard drive. That's represented by this bar at the bottom. And any particular individual row is represented by a single box. When we have a question like, where's Tim? In Badland without an index, this is really slow. We have to scan through every record. And remember, we're talking about typically databases for big companies. We're talking about millions, maybe even billions of records that we have to search through. So this is computationally expensive. It takes a long time. We're going to the hard drive over and over again, which is even slower than just looking through like some data that's in RAM. We don't want to do this. We want to use an index for this. So instead, we build a secondary data store called the index. And this is like a hash table or a B-tree. Those are the two that we'll talk about, as well as the learned index, of course. And we say, we create this data store so that we can, instead of table scan and look at every record in the database, we can ask the index, hey, where's the record I'm looking for? And it will tell us the memory address, offset 7. That's the memory address within our underlying database table where Tim's record is. And we can create these indexes based on, any key that we want. So we can make one with the ID, we can make one with the first name, with the last name, et cetera, et cetera. But they all are extra secondary data structures to the underlying raw data. Okay, and it's a classic example of the ever-present trade-off in computer science research where we spend a bit of memory to create this secondary data store, and by using a clever algorithm and a clever data structure, we can speed up the process, but we have to spend that memory to get there. And this is sign pointing. One of the most interesting things about these learned indexing structures is that classical indexes are quite large and they scale up in largeness as the data that we put in them scales up in size. However, with machine learning models, especially with things like neural networks, we have an incredible capacity to represent data in a smaller format. So if the learned index is trained really well, it's still quite a bit smaller than these indexes, these classical indexes, but still has the capability of answering the question, where's a particular record, really fast. Okay, so that's one of the most interesting avenues that this research opens up, smaller memory footprint indexes. Okay, so that's indexing. There's 5 major concerns when you're looking at an index structure, when you want to say this is a good indexing structure or this is a bad indexing structure. We're going to go through each of these individually, but at this moment in time, I'm going to point out that this paper in question and the learned indexes we're going to talk about explicitly do not look at number 3 and 4. The paper that we're looking at focused exclusively on read-only data sets. So we're never adding new records to the index and we're never deleting records from the index, which is, I mean, honestly, a quite crucial limitation. And it'll be subject to further research in the future. There are certainly some applications for read-only indexes. Things like Bigtable use read-only indexes and just rebuild them, or things like data warehouses, you rebuild the indexes once per night when you get a big data dump. So it's not a killer caveat, but it is an important one. Okay, so let's look at these 5 things individually. First is there's 2 major types of queries, point-to-point queries. Oh, yes, good point from Ron. In addition to inserting a new record and deleting a record, updating a record in a database would also impact the index. If we changed the first name and we're indexing based on the first name, then we need to change the index structure, and that has similar costs, which can also be an issue. Okay, 2 types of queries, point-to-point queries and range queries. There's 2 kinds of things we typically want to do with an index. We want to find out where one specific record is, or we want to find records from a range. Where's the person named Tim, or where's everyone age 5 from 12. Okay, so the 2 structures we're going to look at, hash tables and BTrees, are optimized differently. Hash tables are much better at single point queries, and BTrees are much better at range queries. The lookup speed is obviously important. Once I ask my index a question, how long does it take for me to get an answer back? Typically, we report these in big O notation, classic computer science literature. There's also some good reasons to just measure empirically, because there are things like cache optimizations and other kinds of computer hardware focused optimizations that have been really well studied and long applied to indexing structures. So we'll look at the big O a little bit, but there's other things to keep in mind, just so you know. Okay, so the lookup speed obviously matters. The cost to insert a record, if I have a new piece of data that gets inserted into my database, I also have to update the index. Okay, so the cost there matters. And similarly, if I update an existing record here, I also have to update the index. Deleting an entry from our underlying data store also needs to update the index. If the index says, hey, Tim exists and exists right here at that red dot, and I delete Tim, then my index structure needs to later report, hey, Tim no longer exists. Don't go look at this particular memory location to find Tim's record. Okay. And then lastly, the size and utilization. So the index takes up some amount of size based on the underlying data, because we need to have a data structure that supports us looking up every record or every key in our index. And utilization refers to the information density of this index. So some indexing structures take up quite a lot more space than they need. That means there's empty slots in the underlying index structure that are just waiting to be used. And we call this the utilization. So if we have an indexing structure that has space for twice the number of entries that it actually contains, we say that has a 50% utilization rate. And oftentimes with indexing structures, especially with hash tables, as the utilization rate gets higher, as you get 99% utilization rate, the performance on other metrics decreases. Okay, so there's kind of a trade-off between utilization and some of the other metrics we care about. And there are some caveats when we think about timing these things. Indexing is most important when there's a lot of data. And not only a lot of data, but so much data that you have to put that data on the hard drive. So a lot of these indexing structures are really optimizing for the number of times we have to ask the hard drive for new data, rather than optimizing for the total number of operations. And that's a little bit a benefit to machine learning because we can load these machine learning models into memory, do the inference in a highly parallelized way, and then have it tell us where to go look on the hard drive. So we can still minimize hard drive access while potentially doing many operations, perhaps more operations in total than we might have done with a classical indexing structure. And because these are highly parallelizable computations, there's room for improvement based on, the hardware stuff that I mentioned earlier, like GPUs and TPUs, whereas the classical indexing structures can't really access the benefits of that parallel data inference process. Okay, so that's the basics of indexing. Now I'm going to tell you about hash tables. You've probably encountered a hash table before. So this is the first of the two classical indexing structures that the authors of this paper are comparing their stuff against. And I should say there is also a section in the paper about Bloom filters and an AI alternative to Bloom filters. I'm not talking about that in this talk, but you should look at the paper if you're interested. From Dave, what is the difference between an access and an operation? So let me go back to, let's see, this slide here. Where's the index? Okay, right here. When I'm asking the question, where is Tim? I'm asking this secondary data store, the index, that question. I might do, 10 or so CPU cycles here in the index, which is loaded into memory, into RAM. I might do 10 cycles or so answering that question. A couple of operations to compute the hash code, a memory lookup to find out what the offset is from the data store itself. Whereas down here, this secondary data store where Tim actually is, that lives in the hard drive. And so, your RAM chip and your hard drive are two separate physical devices, and accessing something from the hard drive takes quite a bit longer than accessing something from RAM. That's the whole purpose of RAM, is to serve as kind of a cache of data. I shouldn't use the term cache because there's also a memory cache on your CPU. But RAM is closer to your CPU and faster to access than your hard drive is. So a hard drive access is what I'm referring to when I say access. And when I say an operation, I'm talking about something that can be done in your CPU, like a single floating point arithmetic operation or something like that. Does that make sense, Dave? Awesome. Okay, so with a hash function, which is the primary component of a hash table, well, one of the primary components, you take some arbitrary data and you shove it through your hash function, and then out comes some integer value. And there's lots and lots and lots of different kinds of hash functions, including cryptographically secure hash functions and non-cryptographic hash functions, perfect hash functions, blah, 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 all kinds of stuff. But the most important thing for hash tables, historically, is that this hash function produces an integer which comes from a uniform distribution. Okay, so any integer in the size of your hash table is as likely as any other number to come out. That's a critical piece of information, both for comparing it to the machine learned hash functions that we're going to talk about from the paper, and just for thinking about hash functions in general. Okay, so that integer that comes out of the hash function, which is called the hash code, this integer is called the hash code, is used as a key lookup in your hash table. So your hash table is, a key value pair, essentially, where this integer is the key and the value is the underlying memory address for the record, which is actually in your database on your hard drive. So it looks like this. We ask the hash table, I want to know where Tim's record is. We take that string data, Tim, we run it through our hash function, and let's say the number 15 comes out. And this number 15 is going to be bounded by the amount of space we've already allocated for the hash table. So we allocate that space beforehand. We get this number 15, and we go look at location 15 within the hash table, which is way over here on the right. The value in that location at the hash table is going to be, in this example, it's the number 2, because we are at the 0, 1, 2th offset in the database table. So we do this two-part lookup to find our question. And that means instead of table scanning the database and looking at every record until we found the record that matched Tim, we just did one math computation, the hash function. So, big O1, a constant time algorithm. To compute this 15, we did a single lookup in RAM, which is relatively fast, for this location in RAM, and the value at that location in RAM told us, go to the hard drive at location 2, this location here. We looked that up, we grabbed our data. Boom, that's indexing. Okay, so hash tables are really, really good for individual lookups, but they're poor for range queries. And that's because of the characteristics of the hash function. We have hash functions that just produce more or less random integers as output, random from a uniform distribution. They're consistent. If we put in Tim, we're always going to get back, in this example, we're always going to get back 15 for Tim. So they're not random like a random number generator, but they're from a uniform distribution, and we have no idea. They're random in the sense that we have no idea what Tim would map to beforehand. We just have to compute the hash function and figure out what it is. Okay, so that makes them good for individual queries. We can do this hash code computation really, really fast, but it makes it poor for range queries because there's no correlation between, Tim and tin in our hash function. They just come out to totally different numbers, and they're not at all correlated. So this is very good when you're looking up things just individually, but it's not very good when you're looking up things in a range, which is common for like date queries, or sometimes, you want to look up alphabetical blocks of stuff. Give me all of my users who have a first name starting with the letter A. Hash table would be very poor for that. Query time is O1, so constant time operation. You just do the hash code, do a single lookup, do a single lookup. Boom, really good. Insertion and deletion are also O1, but there's some caveats here that I'll show you on the next page. But similarly, if we delete something or we change something or we insert something, we just add it to the hash table and we say, compute the hash code, go to the location, put it in that location, we're done. The index has been updated. And size and utilization vary a lot based on both the choice of hash function and something called the collision handling strategy. I could talk your ear off about different collision handling strategies like linear probing, separate chaining, cuckoo hashing. They're all very, very cool. But I won't. Mostly I'm not going to, because the way the ML model works, the machine learning version of the hash table works, is that we just use a machine learning model to replace the hash function itself. And the collision handling strategy, we can use any of the known collision handling strategies with the learned hash function just as well as we could with a standard hash function. But I'll say it's relatively common for hash tables to have something like 50% utilization, but some, very high performance hash function or hash tables can perform well even at like 90 to 95% utilization. So look at cuckoo hashing if you're interested in looking at a high performance hash table for high utilization rates. Eric, I see that you raised your hand. Just type your question either into the QA section or into chat, and we'll be able to answer it there. So some gotchas. The collision handling strategy makes a huge difference, but it's not a big problem for the ML models because they can use any of the same collision handling strategies, as we'll see. Like I said, inserts could require you, under some circumstances, to rebuild the entirety of the index. So it's constant time operation most of the time, and sometimes it's a linear operation. Cuckoo hashing is like the bird, cuckoo hashing. So I just typed it into chat for you. From Sanjeev, why is it impossible for the utilization rate to be as high as possible? That's a complicated question, but I can give you some broad strokes. The idea is when you have a higher utilization rate, that is your hash table is more full, every new item that you insert into that hash table is more likely to collide with another item. That is to say, we have some fixed size of our hash table. In this example, we have 15 items in the hash table. And every time we put something in there, we have to deliver a hash code that is between 0 and 15, because, sorry, we've got 16 items here. So between 0 and 15, and if we insert, 17 items into that hash table, then there's nowhere for it to go. We can't have two things sitting at one location in memory. So as you get higher utilization rates, you're more likely to experience a collision where two things need to live in the same bucket. And when two things need to live in the same bucket, you either have to rebuild the entire hash table, or you have to use one of these collision handling strategies that I mentioned, like cuckoo hashing, linear probing, or chaining. And those are higher cost operations because you can't just put the item in, you have to do something to manage the collision. So as you get higher utilization rates, you increase the number of collisions every time you insert a new item, and that degrades your performance overall. Okay, and that's basically this third bullet point. So great, timely question. Okay, so that's hash tables. Now I'm going to tell you about BTrees. I hope this is a fun, super fast little review. So BTrees, the second indexing strategy that's most commonly used, and they're super common for range queries, where hash tables are super common for point queries. So the structure of a B tree is similar to a binary search tree. If you studied those ever, this will feel a little familiar, except with the difference that a B tree has a branching factor of typically about 100. So every node has 100 children. We're just showing 4 children here because I can't fit 100 circles on this slide. So, if you just have 100 items, then you can have a B tree that's only 1 level. If you have up to 10,000 items, then you can have a B tree that's 2 levels. If you have, 1,000,000 items, you can have a B tree that's 3 levels and represent all your data. And the structure kind of grows that way. But it's also a way to represent, like a binary search tree, your data in sorted order. So, the leftmost node, if you go all the way down, the leftmost leaf node is always going to be the first item in whatever your sorted order is. So the number 0 for all the positive integers will live over here. And your last item, whatever it is, will live at your bottom right leaf node, always. Okay. So the partitioning strategy for B trees is such that each node is a list of partition points. So if you're talking about text data, all lowercase text data, this might be an example of a B tree with only 9, items per node, where again, in reality, you'd have more like 100 items per node. But again, we don't want 100 things that just not fit. And so the structure is such that you look at the root node for something that is a relatively fine-grained partition, or sorry, a relatively coarse-grained partition. All the stuff that starts with A, all the stuff that starts with B through D, all the stuff that starts with E through G, and the values at each of these, A is a pointer to whatever the next node in our tree is, and B through D will point to some other node that contains entries only for items that start with the letter B or start through the letters D, and so on and so forth for each of these partitions. If we follow that pointer, say we have something, we're looking for a piece of data that starts with the letter A, then we follow this A pointer and we have further finer grained partitioning. So maybe we start with the first node, everything that is AA, like aardvark, through AB, abs. And then we have a second partition for everything that starts with AC through AD, and then AE through AG, and so on. And then if this is our leaf node situation for the AE through AG, we only have 4 items in our index that match those criteria. They start with the letters AE through AG. Then they might be, Aeon, Afar, Afraid, and Agriculture. And the values in each of these final leaf nodes would point to some data in the underlying database. So these would be pointers to the database tables on your hard drive offsets, just like with the hash table. And we could go fetch all of those pieces of data individually. Okay, so just to kind of, oh, do I have an issue? A, B, C, D, E, F, G, H, I, J, K, L. Yes, you're right. This is an error, Sanjeev. H through L and J through P should not look like that. It should be H through L and then L, M through P. That's a good catch. I should update these slides. So yeah, this is totally suboptimal and actually would break the indexing structure if it actually were allowed to stay that way. This J should be an M, because that's the letter that follows L. I should make a note. Okay, so the process for reading, again, this is optimized primarily for hard drive access. So we're going to do a lot more operations in memory than we're going to do hard drive accesses with a B tree, and more compared to a hash table as well. So the process for this is we read our block into RAM. So that's like the root node, for example, and we iterate over that block until we find a match. And actually, typically, this iteration process will be a binary search over this sorted data. So we'll find which of these blocks to go to, which of our next nodes to go to, and that's just a quick scan. And then we'll read that next block, which would be the next node in our tree, and would repeat this process until we get to the leaf node and find the data that we're looking for. A question from Jay, we'll go back to this chart. If there is no data for M through K, then will there be a B tree node for M through K? This depends a little bit on the specific implementation details. So because of the way the data at the leaf nodes is stored, you want to have, totally sorted data. Sometimes those pages will be allocated. So there will be space for data M through K, but it'll just be empty. And the data M through K situation, if we're looking, or like J through P or whatever, then this table, the internal node for that table, would indicate basically, there are no records, so stop looking. Don't go down any further. But for, thinking about utilization rates, that data may be already allocated. So the page may exist and it might just have empty records, records that indicate, null, there are no matches. Does that make sense, Jay? Cool. Okay, so the performance of B-trees. These are really, really, really good for range queries, much better than hash tables, because if you traverse, if you just look at this, if I want to know what are, say, everything A through G, then I just grab all of these leaf nodes. And similarly, if I want everything AE through AT, I just grab all the leaf nodes associated with these 4 internal nodes. And it's very efficient to be able to do that. For Dave, is there an equal number of items in leaf nodes or equal size ranges in the internal nodes? For most B-tree implementations, the answer to that question is yes. We allocate the size of each individual node based on how much data is fetched from a hard drive at one time. So it's highly optimized, like I said, for hard drive accesses. And your hard drives have relatively standardized block sizes that they'll deliver, and the B trees are built with that in mind. Now, it's not a requirement of the B tree data structure per se, but it is how most B trees are built. And from Senjal, how about a range query AE through AF? How is that filtering handled? Well, then you'd go to this internal node and you would basically scan all the leaf nodes until you met the first leaf node that did not satisfy that query. So we go Eon matches, afar matches, afraid matches, agriculture doesn't match, we're done, just return the stuff before that. So we'd return these 3. Okay, awesome, good questions. Okay, looks like we got a follow-up. So the ranges cannot be too big for table scans to be expensive. Is that right? Yes, the size of these leaf nodes, the size of the nodes are relatively small. We're talking like 512K, I think. Don't quote me on that. I'd have to look it up to be sure, but in the kilobytes range. And also, it's not uncommon. It's not necessarily always the case, but it's pretty common to do the scans of these leaf nodes using binary search. So it might not just be a strict table scan. Yes, Amy, I haven't started talking about the machine learning aspect of this talk yet. These are the 2 classical data structures that are competitive with these new machine learning models. And no, there's not going to be a specific like scikit-learn function for it. But you can use scikit-learn or Keras to kind of build these types of indexing structures on your own. It won't be pre-baked though. Okay, boom, 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 boom. Okay, from Richard, if you have a database that is scaling up, can the B tree be set up to scale dynamically at, say, a given utilization rate? It can't have necessarily a fixed utilization rate, but it can scale up and grow and change. The details of exactly how all that work are a little bit beyond the scope of what I want to talk about today, but there are some interesting resources. You can Google B-tree and you'll get some very great descriptions of how these things scale up and down and what happens when you insert something and delete something, and how you have to change the B-tree. And from Dave, I don't understand what the size of a hard drive block has to do with the number of indices in a leaf node. Okay, so these 4 items are all inside one leaf node. And the size of the leaf node is fixed based on the size of a hard drive block. So there might be empty space in here if you don't have 512K records that match the criteria AE through AG, but the maximum number of entries you would have in a single leaf node is fixed based on that block size. So the space 512K is allocated for this leaf node, and some slots might be null, but you'll have that entire block pre-allocated and nothing else can use that memory. Does that answer your question, Dave? Yes, all of these nodes are often on disk in a major database. So accessing the root node is one disk access, and then you find out which location in disk to access next by scanning through the entries in that node. And if we found out that it's this A1, then and only then would we go back to the disk and load this internal node into RAM from disk. Perfect. Okay, so the query time is log n disk accesses, right? With the caveat that we're scanning the block size every time we do one of those disk accesses. But once we get to the leaf nodes, we've found the answer that we're looking for, and that's, log n queries. Insertion and deletion are log n, but have similar caveats to hash tables. Sometimes inserting and deleting will cause your index to have to be rebuilt or partially rebuilt or rebalanced. And those are complex. Goes back to Richard's question. I don't want to get into exactly how those processes work, but it can cause you to spend more computational time. And then size and utilization varies a lot based on the total size. If you have 9K records, then you can fit them in 3 levels. But as soon as you go over, 10K and 1 records for 100 item nodes, then suddenly you need to build out the entire next row of your B tree and allocate that space. So your utilization rates can kind of vary wildly. It's not easy to say what they are in some kind of a priori way. Some of the gotchas, your B trees, if you don't build them cleverly and smartly, which nowadays it always is the case that they're built cleverly and smartly because you're using some open source implementation, but whatever. If you don't do that, if you try and roll your own, you might find yourself in a situation where you just have a really long chain on the left and you end up with something like a linked list more than an actual tree. So if they're not balanced, then you might not get this O log n performance that you're expecting. Already talked about this, inserting and updating and deleting might cause extra rebalancing operations or cause a node to split into 2 and rebuild your index structure. Okay. So now the machine learning part. Here's a link to the paper again. This is, once again, a Google and MIT collaboration written in 2018. And the key insight of this paper is that hash tables and B trees are just models. Okay, so they're models that map the key of your item of interest to some location in memory, which is also essentially just a regression problem over the CDF of whatever your data is. This is the key insight that sparked the beginning of this research. We can just model a function that accepts a key as, some value between 0 and 1, representing the CDF. Multiply that by the number of elements in our index, and we get the estimated position right back out. From Sanjeev, does the buddy system help with modifying a B-tree? I guess I'm not familiar with the buddy system as a term of art. Maybe it's been too long since I really dug into binary search trees, etc. Do you want to provide a little more detail for me? No problem. Cool. I'll Google it. Maybe I'll learn something. So thank you. Okay, so with this insight in hand, the researchers first set out to just build like a really naive index, and it totally sucked. But eventually, after some experimentation, they came up with some ways to make these machine learning models work better. So one of the first things that they discovered, right, is, and if you do much machine learning research at all, you know this, when we pass something into CDF stands for cumulative distribution function. Okay, what I was saying about one of the first most important caveats of this whole thing is machine learning models are not so great at providing really precise answers. They are getting quite good, though, at providing approximate answers to our questions. Now, with indexes, an approximate answer is not good enough. We need to know exactly where the record is in memory. Otherwise, we can't retrieve the correct record. If we just accepted an approximate location, then every time I asked for Tim's record, I might get, Ted's record or Tin's record or some other record that isn't the record I'm looking for, and that would be actually completely useless. Okay, so this approximate problem is something that we have to solve for machine learning models to be adequately used as indexing structures. So the researchers solved this by having every machine learning model that they use in this way also store its minimum error and maximum error over the training data that was used. And another thing that I'm going to say here, and this is often not the case for ML research, is the training data is the test data in this particular instance, because indexing structures only need to work for data that we've already put into our index. So by the time we create the predictor, we already have all the data that it has to work on, which is quite nice in certain ways for machine learning people, because now not only do you not have to worry about overfitting, but actually overfitting is kind of the goal. You want to fit your model to exactly the data that you have, not some hypothetical data that could come in. Now that's true for these types of read-only in-memory databases, but it's actually a huge problem for databases with write-heavy workloads or any writes at all, because then you have to do something when the new data comes in. You may have to completely retrain your model, and that would be problematic. So this is a place for further research. The researchers didn't try to solve that aspect of the problem, but it is important that we can store this minimum error and this maximum error for every record, not every record, but across the data set that the ML model is trained on. And then we have a bounded problem, so we can get the approximate location in memory and then just go to the database, the underlying database, and search for the record that we're interested in using binary search or some other search. In the paper, they mention a few other strategies that they use, but binary search was generally the most powerful. Okay, from Stephen, wondering what's the difference in overfitting and just building a complete index? Does it help with the next piece of data not in the complete index? In this paper, it's not clear what the answer to your second part of your question is, because they don't even try. They don't even try to think ahead about what data might come into the index. And so if you have a perfectly overfit ML model, it would be a complete index. It would be a perfect and complete index. Now, they had some struggles actually making that happen with the models that they used, at least in competitive timeframes to what classical indexing structures do. But But really, I think in hypothetical terms, there probably wouldn't be a difference. If you had a perfectly overfit model that had memorized entirely the training data, it would be a complete index. Yeah, I wonder why gradient boosting models weren't used as well. They write that they have the most success with small neural networks, 2 hidden layers, only 32 nodes maximum per layer. And actually, we'll see in the next slide, so maybe I should just go there soon. This is what I was saying about bounded guess. They also even use really simple linear regression models sometimes for some portions of the learning problem. Okay, but this wasn't the only problem with this approximate location in memory. So the second aspect of the problem with the approximate location in memory is that machine learning models aren't super precise. It takes a very complex model to say, train 100 million records and get the exact answer to what its position is in the CDF out of 100 million records. So this is the slide that I want to show. So the researchers, instead of building one single large complex model, instead they built a framework and they used something very similar to grid search to build the individual parameters for each of these. But the framework is such that each of these boxes in this image represents a different, separately trained ML model, usually quite small, like I was saying, 2 hidden layer neural networks they used at the top layer of this model. And what happens is a record comes in and the root ML model makes a prediction about which ML model in the layer below me should be used to answer the question, what is the position in memory of this item? And they experimented with a different number of layers in layers of ML models, and they found the most success with just a 2-layer system. At least that's what they report finding the most success with. So one ML model that says, I'm going to pick a separate ML model to go the last mile and predict the actual location in memory. From Rashmi, they did not use random forests, to my knowledge. They experimented with small, simple neural networks, 2 hidden layers, up to 32 nodes total, and they tried a few different numbers. So like, 1 layer with 8 nodes, 1 layer with 16 nodes, 1 layer with 32 nodes, 2 layers, each with 8 nodes, and grid searched the parameter size. But to my knowledge, they did not use random forests. They could, and that would be an interesting area of research to find out which other types of machine learning models might work, especially at each layer of this tiered hierarchical model structure. But they did not try. Okay, and so the whole point of this multi-tiered model is to make it so that you could train simple, very fast inference models that get you part of the way there. So this top model partitions the space into, and I think they mostly found success with about 10,000 simple models in the second layer, which was surprising to me because that's quite a large number. Okay, so this is the framework. They have grid search and a hybridized model approach where all of these models may not be the same type of model. Some of them could be neural nets, some of them could be linear regressions. And in some cases, they even resorted to making some of these ML models actually just standard B-tree implementations. So when there's some kind of distribution that is really, really challenging for their simple ML models to use, they just they threw their hands up and said, let's just use a B-tree to solve this problem instead. Okay, and then the last thing to say, for the non-range queries, for the hash function replacements, point-to-point queries, instead of trying to replace all of the research that's been done on how hash tables work and collision handling strategies, blah, 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 they didn't even bother trying to do that, and they just instead replaced the hash function itself with an ML model that followed the below slides structure, a hierarchical system of multiple ML models. And then this learned hash function is able to take into account the distribution of the data and create a situation where you end up with fewer collisions in the underlying hash table by being able to hopefully take into account the distribution of the data, which standard classical hash functions just by their nature can't possibly do. Yeah, I agree with you, Ron. That's very clever little trick, especially for really tricky distributions. Just fall back on a known good data store. And I think something that sometimes, like the ML purists might frown on, they're like, we should use, just a raw neural network for everything. But I think it's really great to see this combination of some of the really beautiful and great ideas from classical computer science with some of the new emerging really cool ideas from machine learning and statistical computation. From SRV, if I understand correctly, ML is used to replace the hashing functions. Yes, that's exactly right. Okay, so we're getting pretty close to the end of the talk. I'm going to summarize the results of the paper here, and if you want more details on exactly how they structured the loss functions, how they structured the training process for this, complex hierarchical model, I do suggest you take a look at the paper. They do a pretty good job describing it there. But here is what the researchers found, with the caveat that they're focused on mostly small, dense neural networks. They didn't try anything with, oh yeah, I'll resend the link to the paper. Yeah, we will see some comparisons coming up. To Dave, for this research, the hash table was all in RAM. I think they wanted to do more research with, more fair apples to apples comparisons about putting these things on the disk, but they just didn't get to it. They got published this paper after RAM, and I haven't seen anything since then. So all of these are focused on, yeah, right here, create once, read only, in memory data structures. And they just gave up on write heavy workloads. They say that's a problem for the future. We hope this is encouraging enough that some other researchers will take up the challenge and try and solve the problem for write heavy workloads or disk-based indexes. For Sanjeev's question, how is the hierarchy of simple models constructed? On what basis do models get lined up on different layers? Basically the training process that they outline selects this, and it's like almost like a grid search of possibilities. So they build many styles of models that have different, a dense 2-layer here and a linear regressor here and a dense 1-layer here. And they just try many combinations until they found one that worked pretty well on their data set. And then they tested the ones that did best against the benchmarks. So it's not an easy question to answer, but they grid search it. So here's the first findings of comparing 3 data sets. Interesting data sets, and the differences between them are important. But for a B tree of different page sizes to their learned indexes with different second stage model sizes. So again, they have 2 layers, the root node, which predicts anywhere between 10K or 200K second layer simple models. And the data sets are, one is map data, where the key, so it's a map data of just stuff, and the key is the longitude value. So I think they scraped that from something like Google Maps, that like they were working with Google, so they had that kind of data. They describe it in more detail in the paper, but it's just things that exist in the real world keyed by longitude. The second data set is web data, which is web log records keyed by timestamp, and it was for MIT's website. So this is really tricky data for classical indexing structures because it's a very complex distribution that, the schedule of the classes, the schedule of holidays, and all of this kind of weird, hard to predict human stuff goes into the creation of those timestamps. People are looking more, when it's not holiday time, they're looking more when it's time for a final exam. And so more records appear at those timestamps. And then finally, they did a synthetic data set where, they just used a log normal distribution and generated some number of millions of records. So this log normal data is just a totally synthetic data set. And as you can see, the things that I would call your attention to are, look at how much smaller the learned indexing sizes are in megabytes. You know, the smallest B tree is as large as the largest learned index model. So this is a really interesting kind of finding. We can trade a lot less memory for competitive performance. You know, if these researchers, and I mean, like, one of them's Jeff Dean, so they're probably good. They probably know what they're talking about. If they are doing fair apples to apples comparisons, this is promising enough to warrant further research. Their learned indexing structure takes up significantly lower memory footprint and gets on the order of 2 to 3x speed up for this map data, lesser speed up for the web data, which is, you know, very tricky to learn. Just, you know, 1.5 to 2 or so, 1.1 to 2. And similarly, the log normal data only about 1.5, you know, relatively consistently across all the different styles of this model. But certainly worth further research and really interesting to see how small these models are. Okay, so I think that's very exciting. Okay, from their work on the hash tables, not the B-tree range queries, they didn't do any actual comparison to hash tables. Instead, because, you know, like we saw in slide previously, we can use the same hash table underlying structure. So they only compared conflict rates. And if you notice on the map data, quite amazing. You know, only a 7% conflict rate, which means the machine learning models were definitely able to learn the distribution of that underlying longitude data, and so dramatically reduce the number of collisions that would occur. In the paper, they don't have a chart for this, but they do say, and small caveat, the models took a lot longer to compute than the standard hash functions do. So there's still more work to be done here. Inference is expensive compared to a hash function, which is really, it's like 2 multiplications and a shift. It's super efficient. So without accelerated hardware and like using a GPU, this number, the 77.5% reduction, it probably looks a little better than it is. But still, it's really interesting. And especially in the case where a conflict is extremely expensive, this kind of indexing strategy might be very useful. Okay. Finally, well, not finally, there's 2 more. I think I already said this basically. Obviously, models are better at taking the distribution of the data into account, since hash functions and the B-tree structure is built entirely agnostic to that fact. And that accounts for much of the speed up or much of the improvements you could see in the last slide. I already mentioned this earlier in the talk, but one of the things they note is that, you know, overfitting is kind of the goal, at least with the structures that we were looking at, because we're only working on read-only data. So we never have to retrain the model because we're never dealing with writes. I think that's pretty interesting. Since they're table scanning at the bottom between the minimum error bound and the maximum error bound, getting this bound tighter had a bigger impact on performance than getting this guess to be more accurate. So that's another kind of interesting trade-off that you don't necessarily always think about when you're doing ML research. Oftentimes you do, right? But it's not always the goal. Sometimes your goal is really just to get this guess as accurate as possible, especially true with, you know, like classification problems. We talked about this. The standard index grows quite quickly as the data grows, whereas the ML model can stay a relatively fixed size, but still have enough capacity to make reasonable predictions, even as the data grows extremely large. And then finally, there's a better potential for these machine learning models to take advantage of new hardware advances. You know, with Moore's law being dead or dying, CPUs are not getting that much faster. Classic indexing structures are branch-heavy workloads, and you can't easily parallelize it, whereas inference, machine learning inference, especially neural network inference, is highly parallelizable and is driving specific hardware research. Okay, so we might be better positioned with these learned models to take advantage of upcoming new hardware. Another very exciting thing. And then last, this isn't really covered too much in the paper, just in the appendix. We could use this for multidimensional indexing, so we could have keys, multiple keys, first name, last name, age, rather than 3 separate indexes, one for the first name, one for the last name, one for the age. And machine learning models are already, especially neural networks again, really well poised to jump on that kind of an opportunity. They're already good at taking lots of different input, learning some kind of complex pattern match to predict an output, and that might be an area for great and interesting research, say the authors. Okay, I think we're running out of time or over now. Yeah, 3 minutes over. So my name is still Tyler. You can find me at my website, tebslab.com. And on this last slide, I'm also teaching a deep learning class starting on Tuesday. It's focused on computer vision, so you can check out the details at the website here on the page.
All right, thank you, Tyler. That was awesome. And thank you all for attending the talk. Magnimind holds these to hopefully inspire people to further their learning. And if you have paid attention or have participated, you've done that here today. If you haven't already, please make sure, just once again, to subscribe to our YouTube channel and just comment any thoughts in the meetings or today's meeting, or what you think about our new online Zoom format. We also hope that you'll be joining us on April 29th for our talk, Build versus Buy Decisions in Data Science with Daniel Huss. Thank you all and have a good evening.
Thanks, everyone.